This section within software development is very fundamental and very key to understanding how codes can be built and how they must be built using algorithms. And if you're not exactly sure what an algorithm is, it's really just a set of commands that can be used widely to get a desired function to occur. And I'll go into deeper what that means in the next few slides, and you'll see these three are really how you can develop an algorithm. I'm not going to go into any code specific stuff because there's nothing in the manual about anything code specific, and from what I can tell, you don't need to know it. You just need to know how to design a code before writing it. And this is really how you should go about doing it. Pseudocode. Pseudocode is probably what you want to do second. I probably should have switched flowcharts and pseudocode, but it's if you can understand pseudocode, you'll be able to understand flowcharts. And pseudocode is a very simple way of coding. It's not specific. You can't execute it, but it's a good way to really understand how to write something, because every language is going to have some of these things like a while statement, an if statement, um, a repeat, a case. All of these things are common through most of your languages. And this website here, this is a standard that was developed at Cal Poly. So if you would like to go through here, read up on this, it's a very good guide to understanding how to pseudocode. And this is really good if you're writing a language that's tougher, um, like an assembly language where not everything is really obvious. An if statement isn't really if. If you have to put all these different semicolons and stuff, you want to know that your stuff is going to work before you try and code it. So pseudocode is really what you want to do right before you start coding, for real. Flowcharts. Flowcharts are a great way to visualize an algorithm. Um, you can do this with just about any code and any set of things. You can do it for obviously more than code, but flowcharts are key to coding something that's really tricky and not obvious that you can just sit down and write. And it's also a really great way if you're trying to pitch your code to some management or to somebody who doesn't know how to code. So you can't just show them a code and say, yeah, I get all of that. A manager a lot of times will want to see a flowchart and understand what your code's going to do for them. Here's one I found. I think a student for some college wrote it. I referenced his link down there at the bottom under the picture. He wrote a flow chart for finding the roots of a quadratic equation. This is a great example because math functions are key to a lot of code and a lot of algorithms. Most people immediately think of math programs. Obviously, it doesn't have to be. You could have done this with text responses. You make flowcharts like this if you're going to create a call system for people to call in and go through commands. You want to use a flowchart for that. But this is a great way to show how to make a flowchart and an algorithm for something that everyone knows how to do, or hopefully everyone knows how to do. Now, just making a code work isn't all you want to do when you make a code. You want to make it work fast, and you want to make it efficient of the resources. You don't want to burn someone's computer up or make this. You don't want to make a program that finds roots, but it takes 3 hours to find it. That's not going to help anybody. So what I did is over here I made some notes about something you could do to make it efficient. I didn't mean to downplay this guy's flowchart or this guy's algorithm, but there are ways where you can make it faster. So if at the top, rather than going through this first step of a equals 0, going to these different steps, breaking it down, making it so up here you just put in the straight quadratic equation, opposite b plus or minus square root b squared minus 4ac all over 2a deal. If you computed that initially, and if that puts out a real value and gives you a real solution right away, then you're set and you're done. You don't have to do anything else, and the code will be done in one step. Now, if that comes out with some other value, you can do some sort of if statement. So then when it comes off of that, it gives you an error. Or if you're writing in a higher level program that can handle imaginary numbers, then you're also done. You wouldn't need any other steps. But in this case, this is obviously, he's designing this for a program that cannot handle imaginary numbers, because he puts this no root over here, because that would be when you would have an imaginary. So that was my note, was saying that if you immediately executed the quadratic equation, and if that outputs an error or something else, then you would continue down this tree rather than doing it last. Because ideally, if you're doing an equation that can't handle imaginary roots, you might as well assume that the people that are inputting values are going to put values that don't output imaginary roots from the beginning. Scalability. Scalability is key to putting an algorithm that can work across many platforms and many different codes. And so if, let's say I want to write this in C, or I want to write this in like Java or HTML, or not HTML, obviously you can't do that, but something web-based, PHP or anything like that, then you want to design something that you know that anything can handle, and you want to make it handle more stuff, and you want to be able to build off of what you started with. Scalability is a broad term that means moving across platforms and expanding on what you started with. Now, I made some notes on the same flowchart as before, but I mentioned, hey, what if you want to build a program that can handle x to the 5th equation? So you should be able to think about going about that, how to make a tree that can go through and output many different solutions, and you want to give your user as many options as possible. You see, I also mentioned, what if you wanted to show your user imaginary roots? You could create some sort of chain in your tree that calculated, if this occurs, what would your imaginary root be? You could create some other equations that go off of that tree branch there. So there's ways to improve anything, and you want to build a program that you can build onto after you've completed it. So those are things to keep in mind when you're building algorithms in the future. I would go back to this website, read up on this, understand how the pseudocode works. It's really a great resource to use before anyone codes. So, yep, that's where I'll leave you.